People often imagine gravity as a mysterious pull reaching out across space, tugging at objects the way a magnet tugs at iron. That picture is comforting, almost mechanical, but it quietly misleads us. The deeper story is not about an invisible force acting at a distance, but about the structure of reality itself and how matter persuades space and time to behave. Gravity is not something layered on top of the universe. It is written into the geometry of the universe. To understand what goes wrong in common explanations, one must abandon the idea of space as a passive stage. Space and time are active participants. When matter exists, it does not merely sit there and exert influence from afar. It reshapes the very framework in which motion occurs. Objects then follow the most natural paths available to them within this reshaped geometry. What we interpret as falling is simply motion along these paths, which feel inevitable because they are the straightest routes possible in a curved space-time. This is why the notion of gravity as a conventional force begins to fail. Forces push and pull objects away from straight-line motion, but in gravity's case, the straight line itself has changed meaning. A planet circling a star is not being continuously yanked inward. It is calmly following a path that looks curved only because space and time around the star are curved. The elegance of this idea is often lost when gravity is explained using everyday metaphors that rely too heavily on intuition shaped by flat space. Another misunderstanding lies in thinking that gravity is always strong where things are massive. In truth, gravity can be remarkably subtle. Even enormous masses may produce gentle curvature if spread out, while extreme curvature can arise in compact regions, leading to astonishing phenomena such as black holes, where our usual concepts of time and causality begin to unravel. Here, gravity ceases to be merely about attraction and becomes a profound statement about the limits of predictability and the nature of reality itself. What is most striking is that gravity links the cosmic and the intimate. The same principles that guide galaxies also govern the ticking of a clock on your wrist. Time itself flows differently, depending on how space-time is curved, a fact that has been measured with exquisite precision. Gravity, then, is not just about where things go, but about how moments pass, how histories unfold, and how the universe keeps track of itself. When people get gravity wrong, it is often because they expect it to behave like other forces, rather than appreciating it as a redefinition of what motion, space, and time truly mean. And once you really see that, you can't help but grin and say, nature isn't pulling tricks on us with a secret force. It's just letting things move the only way they possibly can. And it's our job to notice how beautifully simple that turns out to be. Most people grow up with the idea that gravity is a kind of invisible hand reaching out and pulling things together. It feels natural because that is how we describe almost every other interaction in daily life. Something pushes, something pulls, something causes motion by exerting a force. But this picture, while useful at a basic level, quietly collapses when you look closely enough. Gravity refuses to behave like an ordinary force because at its heart it is not one at all. It is a manifestation of geometry, a reflection of how space and time themselves are arranged. To see why this matters, imagine motion in the absence of gravity. An object left alone moves in a straight line at constant speed. That idea is so fundamental that we rarely question it. Now introduce gravity, and the naive story says the object is forced to bend away from its straight path. Yet the deeper description says something far more subtle. The object is still moving straight ahead, but straight no longer means what it used to. The presence of mass and energy alters the geometry of space-time, and the straightest possible paths within this curved structure no longer look straight to our everyday intuition. This shift in perspective changes everything. Space and time are not passive containers in which events unfold. They are dynamic and responsive. Matter tells space-time how to curve, and that curvature tells matter how to move. There is no need for a mysterious pulling agent acting across empty space. Instead, motion unfolds as a natural consequence of geometry. Falling, orbiting, and drifting are not forced behaviors, but the most economical routes available in a curved space-time landscape. Once this idea settles in, many familiar puzzles dissolve. Why does an astronaut in orbit feel weightless despite being under Earth's gravitational influence? Because they are not being pulled and resisted at the same time. They are simply following a natural path through curved space-time. Weight in this sense is not gravity itself, but the resistance you feel when something prevents you from moving along that natural path. The ground pushes up on your feet, forcing you away from the straightest route space-time offers, and that resistance is what you experience as weight. Thinking of gravity as geometry also reveals its astonishing universality. Everything, regardless of its composition, follows the same rules. There is no preference for one material over another, no hidden distinction in how gravity treats objects. This is not a coincidence, but a direct consequence of geometry. Paths in space-time do not care what is moving along them. They care only about the shape of the space they inhabit. That simple fact explains why gravity is so deeply woven into the structure of physical law. Perhaps most remarkable is how this geometric view connects the vast and the intimate. The curvature that guides planets around stars also affects the rhythm of clocks and the passage of time itself. Time flows differently in different gravitational environments, not because gravity reaches into clocks and tinkers with their mechanisms, but because time is part of the geometry that gravity reshapes. What we call gravity is inseparable from how the universe measures change. When you finally let go of the idea of gravity as a force and accept it as geometry, the universe stops looking like a machine held together by invisible strings and starts looking like a coherent, self-consistent structure. And then you can laugh a little and admit that gravity isn't some spooky pull after all. It's just space and time doing their job. And we were the ones insisting on calling it a force in the first place. It is tempting to think of space and time as an empty backdrop, a vast stage on which matter performs its motions. In that picture, mass and energy are merely actors moving around, while space and time remain indifferent, fixed, and unaffected. But this intuition turns out to be profoundly wrong. Space and time are not passive, they respond. Wherever mass and energy exist, they alter the structure of space-time itself, changing distances, durations, and the very meaning of motion. To appreciate this, one must first loosen the idea that space is simply where things are, and time is just when things happen. They are woven together into a single fabric, and this fabric I see is elastic in a deeply geometric sense. Add mass or energy, and the geometry changes. Remove it, and the geometry relaxes. Nothing needs to push or pull from the outside. The presence of mass energy is enough to reshape the rules by which measurement and motion operate. What is striking is that it is not only mass that matters. Energy, momentum, pressure, and even stresses contribute to shaping space-time. Light itself, though massless, carries energy and therefore participates in this process. This means that space-time is sensitive not just to what things are, but to how they move and how they store energy. The universe is, in this sense, self-aware at a structural level. Its contents define the geometry, and that geometry then governs how the contents evolve. This relationship is not one-directional cause and effect in the everyday sense. It is more like a mutual agreement. Matter and energy do not sit inside space-time as foreign objects. They are part of the same mathematical entity. When mass exists, space-time cannot help but curve, because curvature is how space-time expresses the presence of mass energy. Asking why mass curves space-time is a bit like asking why angles add up differently on a curved surface. It is simply what curvature means. Once you grasp this, familiar ideas start to look suspiciously shallow. The notion that space is the same everywhere, or that time flows identically for all observers, quietly dissolves. Near massive objects, distances stretch or compress relative to faraway regions. Time itself slows down, not because something interferes with clocks, but because time is locally shaped by the same curvature that shapes space. A clock deep in a gravitational field is not malfunctioning, it is faithfully measuring the time that exists there. This also explains why gravity cannot be switched off or shielded in the way other influences can. You cannot insulate an object from space-time because being somewhere already means participating in its geometry. Mass and energy do not send out a signal asking space-time to respond. Space-time responds simply because they are there. The interaction is unavoidable and universal. Perhaps the most humbling aspect of this idea is how indifferent it is to human intuition. Space-time does not care how strange its behavior seems to us. It curves when mass energy is present, and everything else follows from that with relentless consistency. Our discomfort comes from trying to force this behavior into older categories, like forces and pulls, instead of accepting that the universe has chosen a deeper language. When you really internalize the idea that mass and energy shape space and time, you stop thinking of the universe as objects moving through an arena and start seeing it as a single, interconnected structure. And at that point, it becomes almost obvious. Of course, the universe doesn't need gravity to tug things around. It just quietly rearranges space and time and lets everything else mind its own business. Once the geometry of space and time is allowed to change, motion itself must be rethought from the ground up. The usual idea that objects move because forces act on them becomes an approximation, not a principle. In the deeper description, objects simply move the way geometry permits them to move. They trace paths that are not chosen, not calculated, not negotiated, but dictated by the shape of space-time itself. These paths are the straightest possible routes in a curved world, even though they rarely look straight to us. In ordinary flat space, a straight line is easy to define. It is the shortest distance between 2 points and the path that requires no steering. But once space-time is curved, straight takes on a more subtle meaning. An object that feels no force at all, no push, no pull, no resistance, will still follow a curved trajectory if space-time itself is curved. That curve is not a sign of interference. It is the natural consequence of geometry. The object is doing exactly what it would do in empty space, moving freely. This idea explains why gravity feels so peculiar compared to other influences. A charged particle under an electric force can tell that something is acting on it. It accelerates in a way that depends on its charge and mass. But under gravity, all objects move the same way when no other influences intervene. A feather and a stone, once stripped of air resistance, trace identical paths. That universality is not an accident. Geometry does not discriminate. The paths available in space-time are the same regardless of what travels along them. Consider a planet orbiting a star. The traditional picture suggests a constant inward pull, endlessly redirecting the planet from flying off into space. But the geometric view replaces this with something calmer and more elegant. The planet is simply moving forward through time, following the straightest path available. Because space-time is curved around the star, that straightest path closes in on itself, forming an orbit. No force is needed to keep the planet moving that way. T would take a force to make it do otherwise. This also clarifies why free fall feels like weightlessness. When you fall, you are not being dragged downward by gravity in the usual sense. You are being released. You are allowed to follow a natural path through space-time without obstruction. The sensation of weight arises only when something prevents that motion, when the ground or a chair pushes back and forces you off the path geometry is laid out. Weight, then, is not a sign of gravity acting, but of gravity being resisted. What makes this perspective powerful is that it applies everywhere, from the quiet drift of dust grains to the violent plunge into a black hole. Near extreme curvature, the paths available to objects become increasingly strange. Time itself tilts towards certain directions, making some futures unavoidable. Yet even there, nothing mystical is happening. Objects are still doing the simplest thing possible, following the geometry. This way of thinking demands a certain humility. It asks us to stop imagining nature as constantly pushing and pulling things around, and instead accept that the universe has built-in instructions for motion. Geometry replaces force as the guiding principle. Motion becomes less about causes and more about consistency. And once you finally get used to that idea, you may find yourself smiling at how little effort the universe actually expends. Things aren't being yanked along invisible strings at all. They're just cruising along the only roads space-time gives them. And it only looks dramatic because the roads themselves are bent. The idea that motion requires a continuous force is one of the most stubborn habits of human intuition. It comes from everyday experience, where friction, air resistance, and constant interference dominate everything we see. If you slide a book across a table, it slows down unless you keep pushing. From this, it feels obvious that a planet circling a star must be constantly pulled inward to stop it from escaping. Yet this conclusion mistakes an artifact of our environment for a law of nature. Remove resistance and motion reveals its true character. An object left alone does not yearn to stop, it continues. No effort is required to maintain motion, only to change it. Once this is understood, the picture of an orbit as a perpetual struggle between motion and attraction becomes unnecessary. The planet is not fighting an urge to flee. It is not being corrected at every moment by an invisible hand. It is simply moving freely. The key is realizing that free motion does not mean straight lines in the everyday sense. In a curved space-time, free motion traces paths that may loop, spiral, or bend. An orbit is not evidence of a force acting without rest. It is evidence of geometry doing its job quietly and consistently. The planet follows the straightest possible path available to it, and that path happens to circle the star. This way of thinking resolves a deep confusion. If gravity were a force in the usual sense, one might ask where the energy comes from to keep pulling forever. Forces typically involve exchange, expenditure, or mediation. But in orbital motion, nothing is being spent. The planet is not losing energy simply by orbiting, and the star is not supplying energy to keep the motion going. The system persists because nothing needs to intervene. What often gets mistaken for a force is really the refusal of space-time to be flat. The curvature sets the rules and motion follows. This is why orbits can be stable for billions of years without any mechanism working behind the scenes. Stability is not enforced, it emerges. The geometry allows certain paths, and once an object is on one of them, it stays there unless disturbed. This also explains why altering an orbit requires an active push. To move a satellite into a different path, engines must fire. Energy must be added or removed, not to balance gravity, but to force the satellite off one natural route and onto another. Gravity itself is not doing the work, the engines are. Gravity merely defines the menu of possible motions. The elegance of this picture becomes even clearer when you consider systems beyond planets. Rings around galaxies, streams of stars, and even light itself all follow similar principles. Light bends near massive objects not because it is pulled like a stone, but because its path is constrained by the same geometry. It follows the straightest route space-time allows, even when that route curves around a massive body. This perspective demands that we abandon the idea of gravity as something busy and energetic, constantly acting. Instead, gravity is patient. It does not push, it permits. It does not compel motion, it shapes the arena in which motion unfolds. The drama we perceive comes from our insistence on thinking in terms of forces, when the universe is content with geometry. And when you finally let go of the notion that orbits need to be held together by a continual pull, it feels almost embarrassing that we ever thought otherwise. Nothing is working hard. To keep things circling, they're just moving freely, and space itself quietly curves to make that freedom look like attraction. When gravity becomes extreme, our comfortable ideas about space, time, and cause and effect begin to fray. In gentle situations, curvature is subtle and forgiving. Paths bend slowly, clocks drift slightly, and the universe behaves in ways that can still be approximated by older intuitions. But compress enough mass or energy into a small enough region, and geometry stops being polite. Space-time twists so severely that familiar concepts no longer apply in the ways we expect. In such regions, gravity is no longer just about motion through space. It becomes a statement about the structure of time itself. The distinction between where and when blurs. Directions that once pointed freely outward begin to tilt inward, and what used to be a choice of motion becomes a necessity. Near these extremes, the future is no longer an open landscape, it funnels. This is where the idea of predictability encounters its limits. In ordinary physics, knowing the present with enough precision allows you to calculate the future. But when curvature becomes too intense, the very notion of a well-defined future can fail. Certain regions of space-time seal themselves off, hiding what happens inside from the rest of the universe. From the outside, events beyond a boundary become fundamentally inaccessible, not because we lack technology, but because space-time itself forbids the information from returning. These extreme situations reveal that gravity is not merely another interaction layered onto reality. It is the framework that decides which questions can even be asked. In strongly curved regions, time may slow dramatically relative to distant observers, effectively freezing processes from an external point of view. Yet locally, nothing strange seems to happen. Physics continues normally for those caught in the curvature, even as the outside universe watches their clocks fade into stillness. What is unsettling is not the violence of these environments, but their logical consequences. Cause and effect, which we rely on as a basic ordering principle, can become ambiguous. Paths through space-time may end abruptly, not because something crashes into a wall, but because time itself runs out. The equations still speak, but they no longer tell a complete story. They describe evolution up to a point and then fall silent. This silence is not a failure of mathematics. It is a hint that our understanding is incomplete. Extreme gravity exposes cracks between our best theories. Geometry handles curvature with elegance, while quantum principles insist on uncertainty and discreteness. When gravity becomes overwhelming, these two languages collide, and neither remains fully trustworthy on its own. The universe, it seems, is keeping a secret at precisely the places where gravity is strongest. Yet even here, gravity remains true to its nature. It does not act violently in the usual sense. It does not smash objects together out of malice. It simply reshapes space-time so drastically that ordinary motion and ordinary time cease to make sense. The drama comes from geometry pushed to its limits, not from an aggressive force at work. These extreme cases matter because they reveal the boundaries of our concepts. They show us where words like before, after, inside, and outside lose their sharpness. Gravity, at its most intense, is not just telling matter how to move, it is telling us where our explanations stop working. And when you step back and look at it that way, you can't help but feel a mixture of awe and irritation, because gravity doesn't break the rules when things get extreme. It exposes the fact that the rules we were so confident about were only provisional all along. Gravity is usually introduced as a story about motion through space, about falling objects, orbiting planets, and the way masses influence trajectories. Yet one of its most profound effects has little to do with where things go and everything to do with how time passes. The flow of time itself is shaped by gravity, and this fact quietly undermines the idea that time is a universal, ever-ticking background shared by the entire universe. In everyday life, time feels uniform. A second here seems identical to a second anywhere else. That assumption works well because Earth's gravitational field is relatively gentle, and we move slowly compared to the speed at which light carries information. But once gravity is taken seriously as a feature of space-time, the notion of a single cosmic clock dissolves. Time becomes local. It belongs to places, not to the universe as a whole. Where gravity is stronger, time passes more slowly. This is not because gravity interferes with clocks or drains their energy, but because time itself is part of the geometry being reshaped. A clock does exactly what it is supposed to do. It measures the time that exists where it is. If two clocks experience different gravitational environments, they are not disagreeing about time, they are faithfully reporting different realities. This realization forces a dramatic shift in perspective. Time is no longer an invisible river flowing evenly everywhere. It is more like a terrain, sloping and curving depending on the distribution of mass and energy. Near massive objects, time sinks. Far away, it rises. Motion through time becomes as dependent on position as motion through space. What makes this especially striking is that it is not a theoretical curiosity. The effect is real, measurable, and unavoidable. Clocks at different heights tick at different rates. Systems that rely on precise timing must account for this or fail. Gravity does not merely influence motion, it sets the tempo of existence. This also reveals why gravity feels so deeply connected to causality. Cause and effect are ordered by time, and if time itself is flexible, then the structure of causation becomes dependent on geometry. In strong gravitational fields, the ordering of events can shift in ways that challenge intuition. What appears simultaneous to one observer may not be so to another. The universe does not insist on a single narrative. It allows many, each consistent within its own space-time context. The connection between gravity and time also explains why extreme gravitational environments are so unsettling. As curvature increases, time slows dramatically relative to distant regions. From afar, processes appear to grind almost to a halt. Yet for those within the field, nothing feels abnormal. Life, motion, and thought proceed normally. The discrepancy is not an illusion, it is a feature of reality. Time is doing different things in different places. This shatters the comforting idea that time is an absolute backdrop against which physics unfolds. Instead, time becomes an active participant. Gravity does not act within time, it sculpts time. The ticking of the universe is not synchronized and never was. Once this is understood, gravity stops being just a story about falling apples and orbiting planets. It becomes a statement about how the universe keeps track of change itself. Space tells matter where it can go, and gravity tells time how fast it is allowed to pass. And when you really take that in, it's hard not to laugh at how casually we talk about time flowing, because gravity has been quietly adjusting the speed of that flow all along. And we only noticed once we bothered to build clocks precise enough to catch it in the act.